Hello, this is Nicholas, and in the last video I outlined the mechanism for the second partial derivative test and how to actually perform it. In this video, I'm going to be actually proving the second partial derivatives test. And so I asked to start by considering the following. I'm going to consider... and make sure you've watched my directional derivatives video or you know about them for this proof, because that's kind of what the proof is centered around. So we're going to consider the directional derivative of the directional derivative of f of x naught comma y naught. So in other words, the second directional derivative at the point x naught comma y naught. And of course, for u being a unit vector, so its magnitude is therefore 1. And so what can we say about the directional derivative of the directional derivative? Well, we know, I'm just going to write it as, there's three different cases. If d sub u of f, I'll write it like that, is greater than 0, for the x naught y naught there. If it's greater than 0, then we've got a concave up in every situation, right? The directional derivative is greater than 0 in every direction. So that means that our rate of change, our tangent vector, would be going something like that, right? And so we would then have a local minimum. And very similarly, if d sub u of d sub u of f is less than 0, then we're going to have concave down in every direction, and so therefore we'll have a local maximum. And then the last situation is if d sub u of d sub u of f, it could be greater than 0 in some directions or less than 0 in other directions, which would imply that we have like positive concavity if we approach along one direction and negative concavity if we approach along another. So that means we have differing concavities depending upon the direction we approach, and that is defined to be a saddle point. So these are our three different cases here that we need to consider. So let's actually consider what d sub u of d sub u of f is. So if we have d sub u of d sub u of f for our unit vector, which I'll call having components h and k. So now, first of all, remember that just the directional derivative of f, not the directional derivative of the directional derivative, that's defined, well, not defined, but an equivalent definition is the gradient of our vector f dotted with our unit vector u. So that gives us the vector f sub x, f sub y, if we're dealing with functions with two independent variables, in other words, of the form z equals f of x, y. Dotted with our unit vector, which is h comma k. And so, definition of the dot product, we get f sub xh plus f sub yk. Okay. Now, to take the directional derivative of this here, what we need to do is we need to find the gradient, or let me write it, at d sub u of d sub u of f would then be equal to the gradient of the vector f sub xh plus f sub yk dotted again with our unit vector u. And then that will be dotted that'll be dotted with the vector h comma k, because remember we have to dot it twice here, since we're taking two directional derivatives. And u is h comma k. So now, when we do this, we get the vector, we're taking the partial derivative with respect to x of this, and then the partial derivative with respect to y of that same thing. So we get the partial with respect to x of f sub x h plus f sub y k, comma, the partial with respect to y of f sub x h plus f sub y k. And then that will be dotted with h comma k once again. So then applying the definition of the dot product, we're going to get the vector. Well, first I'll take the partial derivative. I'll break it up, take the partial derivatives first. And I'll use a little nicer notation. So we get f sub x x h, so the second partial derivative with respect to x, plus f sub x y, or f sub y x, doesn't really matter because we're assuming continuity. But let me write it as f sub y x. That's better notation. K, and then we take the derivative now of that component, and so we will get f sub x y h plus f sub y y k, and that's still going to be dotted with our unit vector h comma k. So now we take the definition of the dot product again. That was weird, my pen just like went wonk on there. So now, after some algebra, it turns out you get f sub xx h squared plus 2 f sub x y hk plus f sub y y k. Oh, f sub y y, I forgot the second y, k squared. And so what I did was I combined this and this, because f sub yx and f sub xy are assumed to be the same since we're assuming continuity. So Clairaut's theorem applies. Okay, so you might notice this and kind of say, well, this piece here that we've just found, it kind of looks quadratic-like, if you will. So let's kind of force it to become that. So let's consider g of t to be f sub xx t squared plus 2 f sub xy t plus f sub yy. And we're going to let that be a t squared plus b t plus c. So in other words, f sub xx is a, 2 f sub xy is b, and f sub yy is c. So, and then this will all be, again, just to make sure we aren't losing track of what we're actually doing, this is all at the point x naught comma y naught. Okay, so the discriminant then of this like pseudo quadratic, if you will. So we usually in multivariable calc we call the discriminant this delta. So it's obviously it's b squared minus 4ac, and so the discriminant will be 2f sub xy squared minus 4 f sub xx f sub yy, and that turns out to be 4 f sub xy squared minus 4 f sub xx f sub yy. Okay, and what we can do is we can, if you remember, this looks very similar here to how we had our d operator in the last video, where I defined the d operator of a point x naught comma y naught to be, it was f sub xx f sub yy minus f sub xy squared. So looking at this and looking at that, it would make sense to factor out a -4 from this, and then we could just make the rest of it the d operator introduced in the previous video. So what I'll do is I'll make this just -4 times d, where d is this operator right here. So now, if we've got some cases to consider here. So if d, our differential operator here, is greater than 0, and f sub xx is greater than 0, then we have that since d is greater than 0 and f sub xx is greater than 0, then that would mean that the discriminant b squared minus 4ac would be less than 0, because we have this -4 out front here. And that would mean f sub xx is greater than 0, which would mean that our coefficient a in our pseudo-quadratic here is also greater than 0. So this a, this f sub xx is greater than 0, is what we're assuming. So now, this means that we would have, like, if you imagine actually like graphing this quadratic, so we have the situation where it's opening up and its discriminant is negative. So that means it's got positive concavity but no real roots. So it would look something like that, right? I don't know. It doesn't really matter what plane this is in. It just matters so much that this is above the x-axis. So that means g of t is greater than 0 for all values of t. So if we consider then g of h over k, then what we get is, obviously we just plug in, we get a times h over k squared plus b times h over k plus c, and that's going to be greater than 0. And so that implies that if I take k squared and multiply it by g of h over k, what I get is that k squared g of h over k. And by the if you kind of forgot where the h and the k were, they were the components of my unit vector. So k squared times g of h over k is giving us that we would get ah squared plus bhk plus ck squared, and that's going to be greater than 0. And so what that means in terms of a, b, and c, actually what a, b, and c are, we would get that f sub xx times h squared, because that is a, plus 2 f sub xy times hk plus f sub yy times k squared. And then that's still going to be greater than 0. And so this actually proves case 1 now, because what this means is that the directional derivative is always going to be positive in every direction. So it's always going to be greater than 0. So this means that we always are going to have positive concavity, right, for any h and k. And so therefore this implies that this first case is done. The second case is done very much the same. The only difference here would be now that we would be assuming that f sub xx, and we could have used f sub yy throughout this whole proof instead, it doesn't really matter. But I just picked f sub x since that's the leading coefficient of the parabola, if you will. So, and the only difference here with case 2 would be, where did I write it? We would be assuming f sub xx to be less than 0. Oh gosh, where did I write it? Okay, yeah, so right here. We would just assume it to be less than 0, and then the b squared minus 4ac we would also assume to be less than 0, and so that means that a would be greater than 0. And then right here we would just have a flipped equality sign, and then right here as well, and then likewise here as well. And so that also takes care of case 2. It's the same exact logic. In case 2, you have the case where you have a parabola opening down like this, and so it always is below the x-axis for all values of t. So it also has it's always going to be negative, and so therefore the directional derivative will always be negative, so we always have negative concavity, which implies a local maximum. Okay, so the third case that we need to consider is if, case number 3, if we've got d being less than 0, then what this implies is that b squared minus 4ac is greater than 0, right? Because we had a negative 4d, so the sign gets flipped there. So b squared minus 4ac is greater than 0. That means that we have some roots, right? We have this quadratic intersecting. So that means that I'm going to write it like this. There exists, that's the set theory symbol for there exists. So there exists some t such that g of t, let's call it g of t sub 1 is less than 0, and another t, I wrote and g of t sub 2 is greater than 0, and t those are the roots of this pseudo parabola, if you will. So we need to find a unit vector u sub 1 to be have components h sub 1 comma k sub 1, for which the double directional derivative, so d sub u sub 1 of d sub u sub 1 of f is say less than 0, and simultaneously unit vector u sub 2 being h sub 2 comma k sub 2, for which d sub u sub 2 of d sub u sub 2 of f is going to be greater than 0. And so that means we have differing concavities there. So again, let's consider, just like how we did here, where we plugged in h over k, let's consider t sub 1, t sub 1 to be h sub 1 over k sub 1. Okay, and so assuming that this is a unit vector, then we would have h sub 1 being t sub 1 over the square root of 1 plus t sub 1 squared. And then k sub 1 being, say, 1 over the square root of 1 plus t squared, t sub 1 squared. And these two things right here, this h sub 1 and the k sub 1, just make sure that our unit vector is actually a unit vector, right? Because if you were to square this, and then sum them up, you would just get t sub 1 squared plus 1 over t sub 1 squared plus 1. And that just gives 1. So it is a unit vector there. So those are just components. I could have picked any components that make it a unit vector, but I just decided to pick those. So now if we consider, if we consider g of h sub 1 over k sub 1, that's going to be equal to, obviously, a times h sub 1 over k sub 1 squared, plus b times h sub 1 over k sub 1, plus c. And so, same logic as before. If we multiply by k sub 1 squared times g of h sub 1 over k sub 1, what we're going to get is that f sub xx, right, plugging in my definition for a now, f sub xx times h sub 1 squared plus 2 f sub xy, h sub 1 k sub 1, plus f sub y times k sub 1 squared. And all of that is going to be less than 0, right? Because we assumed that this is the first case, this is like the first subcase of case 3. This is the part where we assumed g of t sub 1 to be less than 0, so this whole thing is going to be less than 0. Okay, and so similarly, I'll just write similarly because using this exact same logic, we would find a t sub 2. So all right, there exists t sub 2 such that f sub xx, let me write it here for better comparison, f sub xx times h sub 2 squared plus 2 f sub xy h sub 2 k sub 2 plus f sub yy times k sub 2 squared is times I was getting ahead of myself, k sub 2 squared is greater than 0. And so this implies that the directional derivative of the directional derivative of f could be either less than 0 or greater than 0. And so that implies that depending upon which direction we approach, we get positive or negative concavity. And so that means that we have a saddle point. And so again, that implies that the third case as well as the second case are now done because, again, we have written this proof in terms of our operator D, and so that takes care of the second partial derivatives test. This, by the way, is not the more general way to prove it. I am honestly not familiar with the more general way. It involves this D here is, if you recall, f sub xx, f sub yy minus f sub xy squared is just a special, it looks like a determinant, right? It's the determinant of the matrix f sub xx, f sub yx, f sub xy, and f sub yy, which is just a 2x2 Hessian matrix. Oh, it's almost full. Better stop recording soon. And so that would just be, this is just a special case, in fact, of a more general Hessian matrix. I know the proof involves some eigenvalues of this determinant. So if you're familiar with eigenvalues and eigenvectors, go right at it. Multivariable calculus is normally just concerned with generalizing this to just functions of two independent variables because the complexity kind of explodes after that. I hope this video has been good for you. I remember when I first learned it and I could not find a rigorous proof of the second derivative test. So I hope this proof has been very rigorous for you and that there has been no step where you have been lost and